So, as every week, we do a quick overview of the most important stuff from the lectures. Of course, as always, this is not the only thing or the only stuff you need to know, but it gives you a good overview of the important topic areas and of course the most important topics inside of the areas here. So, we've talked about file systems all week. All the videos were about file systems all week. So we started with looking at files in Unix, like file abstractions, how to handle files in Unix, how to manage lots of files in file systems. We looked at virtual file systems and mounting file systems. And then we looked at simple ways to implement file systems. So contiguous storage, fat files, index storage, and tree-based storage. And then we had a closer look at free space and directory management. Now, all of these simple file storage management methods are old. They are from the at least 1970s or 80s. So, of course, we had some more recent developments in there too. And since these are quite important in terms of reliability and performance, we discussed these in a separate lecture. So we looked at modern file systems and the challenges. We looked at the Unix buffer cache. So how do I actually hide the latencies of disk accesses, improve the throughput by caching again, like in the CPU cache, we can also cache, data coming from a disk. And then we looked a bit at what happens if we want to go beyond a single disk. So we looked at logical volume management and then at RAID, so at disk arrays to improve performance, so reduce latencies, increase bandwidths, but also increase reliability of disk drives in an inexpensive way. And finally, we took a look at more recent developments in file systems like journaled log structures and copy on write file systems. So you've probably all seen this thing mentioned about Unix that says in Unix, everything's a file. So a file obviously is a very important concept in Unix system. So the good question is like, what is a file and why are we using it? Now, we could enable a user to directly read and write blocks from a disk, but this would have quite a number of problems. Now, first is, of course, every application would have to administer where it stores its data on the disk. Second, all applications would somehow have to coordinate which application stores its data in which part of the disk. And of course, then we would need to find other methods to ensure security. So to just constrain one application reading blocks from a certain range of the disk and another application reading blocks from another range of the disk. And then we'd still need to find a way that is hopefully unique across our whole operating systems and applications to identify files. So how do I find files? Are they just one big heap with a name, or are they just numbers? Or do we have something like a directory hierarchy? How are these directories separated when I enter them, like using a slash or a backslash? Or there's other conventions like colons or greater than signs in different operating systems. So it's a good idea to have files to provide a logical view on data that's permanently stored, not only for applications, of course, for applications, but of course also for the user, because it's much easier for the user to remember, oh, I saved my work in master thesis May 2022.tech instead of block 650 to block 722 of this too. So obviously files help you to abstract from storage location and attributes of files. This metadata, the first, of course, is a name for the file, helps you to remember and figure out what's inside of that file. And then you have additional metadata like the owner, so you can have access controls, access permissions. You can have an access date. You can also monitor a modification date, so you can figure out when was the last time this file was modified. And there can be additional flags, like in fat file systems, there's a bit that indicates if a file has recently been backupped, for example. And this file abstraction also enables you to leave this concept of a disk behind when you want to store information, because now file accesses just take place using a name and maybe a path somewhere in the system. And this enables you to store your data completely somewhere else. This might be something simple like a RAM disk, so a temporary storage of data in RAM, which is of course much faster than storing data on disk. So you split your RAM between RAM you can use for your applications and RAM that's actually used to simulate a disk. Or you can have network file systems, so you can have a storage server somewhere and you actually access the files over the network. Now, very early versions of network file systems were really something like a virtual block device. So essentially, you sent block numbers for that virtual disk over to the server and got blocks returned. And people found out relatively soon that that's not the way to do it. Usually, there's still some systems doing this, like for iSCSI, for example. There's relatively low-level approaches, but many file accesses nowadays, for example, with NFS, the Unix network file system from Sun, or the Samba or Windows remote file systems, they actually use file names and offsets inside of files, and the file server then can decide where and how to store data, and you as a user and your application doesn't have to take care of that. It also enables virtual file systems that have no backing storage at all, like the proc file system in Unix, for which you can use to access structured information about your system, just using path names like you would use them for regular files. So we have said in Unix everything's a file, which means every resource in the system. We've seen a file, we've seen proc information. We also have things like special device files, which we can use to access devices. Every resource in the system can be accessed using a name, and this name is mapped into a directory hierarchy, and this name is combined with all the metadata we've seen before. So very often you map this down to blocks on disks, but this doesn't always have to be the case. And the important thing is you and your application doesn't actually have to care about where this file is stored, because it's all accessed in a uniform way. Now, unfortunately, in Unix, this breaks down relatively easily, and especially when you do network access. So you cannot just access a web page by, for example, using a path /net /http /tcp /port 80 whatever name of the server path of your web address. You've just written a web server, just writing it. So you know a bit how this works. So we have the socket calls. We need to add calls to open a socket or to receive a connection on a socket, instead of just using them absolutely identically to file operations. Now, of course, this has also concerned the Unix developers. So in these follow-up projects to Unix I probably mentioned before, like Plan 9 and Inferno, you can actually have resources distributed all over a network. So these systems are network aware, and you can actually have paths in the way I described before, just accessing remote resources on a Plan 9 system, or even somewhere on a web server, which is running a completely different operating system. Unix did mostly not reintroduce this for, well, compatibility reasons. So all of the applications you use accessing data on the internet is using sockets, and even Windows adapted sockets. In early versions in Windows 3, it was an add-on product from third-party vendors, like there was a product called Trumpet WinSock, which was in wide use before Microsoft actually could be bothered to implement their own TCP/IP stack. And even in products like Windows 2000, so the second version of NT, more or less, they still used large parts of the BSD Unix source code to implement their sockets network stack for TCP/IP before they rewrote it, I think, around Windows XP to, well, build their completely own network stack. Nevertheless, everything's a file works still for most things, and that's still pretty nice and convenient for us. So we've seen ways to access files in Unix. So there's an API, an application programmer interface, and we see that file names are not that relevant if you want to use them inside of your application. So once you open a file, if this open is successful, so the file exists, you have access permissions to that file that at least conform to your access rights you want, so read, write, or whatever. And then you are returned a file descriptor. So file descriptor for our purposes is just an integer number. And these integer numbers are unique to the process opening or closing files. So this means we have some standard file descriptors like 0, 1, and 2. We've seen them before. Standard input, standard output, standard error channels. And if we keep them open, so these are for communicating with your terminal session, if we keep them open, the first file that would be regularly opened would usually receive the file descriptor 3. So that's the first unused one. This means that the operating system has to provide a mapping from these file descriptors, which are process specific, to files in the system, and this is done somewhere in the process table. So essentially, there is a mapping from the file descriptor that's open in your process table entry, to the inode or to the file that's actually currently link to that file descriptor. Of course, this link can change if you close the file descriptor and open one again. Then, well, you could just use this file descriptor to access a different file from that point on. So you have open and a related close call, and open, yeah, returns a file descriptor. If it's successful, close informs the operating system that you no longer want this file descriptor to point to that file, and then the common operations for operating on a file are read and write. So read and write always use a buffer in the process memory. So there's a pointer buff that's passed as a second parameter. The first is always a file descriptor, and the third parameter is the number of bytes in your buffer. So of course, like with all C programs, reading and writing the buffers, you have to take care, for example, that you actually pass a pointer to a buffer that's big enough for a write operation. So your number of bytes should obviously not be larger than the size of the buffer. If that happens, you're going to overwrite some other information in memory, which usually is hard to debug. And there's a large number of supporting functions. I'm not going into details on these. So we have, for example, functions like access to give you information about access permissions. You have a stat call giving you current information about like who's the owner of that file, what are access permissions, what's the size of the file, modification times. You have the infamous system call create without an E at the end. So it's just spelled create, which is used to, as the name says, create a new file. And for whatever reason, the original Unix developers said that it was their biggest mistake they did when designing Unix to leave out the E in create. Well, that is debatable, obviously. So when you have files in different file systems. So for example, you can have different file systems on different disks. You can also split up a disk into different file systems. Yes, they fixed the create name finally in Go, thanks. Yeah, they learned like 20 years later. So we have different file systems. We can partition a disk into different contiguous areas and assign a file system to each of these. And we can have virtual file systems like the proc or the sys file system in Linux. And what we want is we want to get away from what you've seen in Windows or DOS, that you have all these drive letters. So you have A and B for floppy drives, and C is your first hard disk usually. And then when you have network drives, it's a bit crazy because you still have to assign them a drive letter as if they were a physical device. So Unix does this differently. So in Unix, you have a single root for your file system. And then in the single root, well, there are usually things mounted. So in the root of your file system, there's one file system mounted. And under this file system, you have directories, and you can mount additional file systems under these directories, as we call it. So as we see on the right-hand side here, we can have a second file system on a disk partition def sda1. So def is our, again, a directory, which can be a real directory or even a virtual directory, depending on your operating system. And this directory contains usually device nodes, so special files that are linked to a device. SDA stands for SCSI disk. Well, nowadays SATA disks are also called SDA, so you could also call it SATA disk. Nowadays, A is the first disk, and 1 would be the first partition. So you have a partitioned disk SDA, so your first SATA disk in your computer is partitioned. The first partition contains a file system, and you want to have it in your file system hierarchy. So you call mount, a system call, with giving it the name of dev SDA1, and then you tell it where you want to mount it in your hierarchy. So in /srv, so this directory has to exist when you execute the mount call. And then you also have to give it information about which file system type, for example, it contains, like XFS or whatever. And then everything that was previously underserved, if this directory was not empty, is shadowed. So it's not deleted or something. It's just not visible as long as you have this mount active. And what's visible in surf is the root directory of that file system on SDA1. And then all the directories below this, like www, svn, and so on, are available under surf. And you can, in parallel, have regular directories with other directories or files inside of that root directory. And of course, you can mount things in other places here. So what a Unix system usually does when it starts up, there's a file system table in a file called etc/fstab. It's just a text file, so you can check it out. And this fstab, so file system table, indicates which file systems should be mounted at system startup. So that's the root file system, that's probably the proc file system, the sys file system, and maybe other additional partitions you define. This is enabled by having this virtual file system structure, where essentially you can add links to other file systems in your file system hierarchy. And this works because all file systems which are part of the OS kernel in a monolithic OS have to implement the same API. So essentially, as an application, you don't actually notice that suddenly a file is on a different device, on a different file system. Of course, you notice it using different parameters, like if your root file system would be on a fast SSD and your file system SDA1 would be on a slow hard disk, you could notice it due to the access times, or if it would be on a network file system, it might be even slower. So some virtual file systems like proc or sys are not backed by storage. So information in this is generated on demand. So you enter proc, you have an entry for each process currently running in the system, just a directory that, like shown in the top right-hand picture here, gives the process ID like 12 or 34. And then under this, there's more information. You can just cd into proc and then a process ID, and then you can use cat to look at some of the stuff like proc command line. And you can try it out. You can't really destroy anything using this. Now you can destroy or change things when usually you're root and you want to figure out or change things. You can actually write to these virtual files at proc and sys in order to change some parts of your system configuration at runtime, which is quite convenient. So we looked at simple file storage. So first, contiguous storage, where you just need to find a range of 3 blocks on your disk that's big enough. And then you notice, okay, at block 2, my file starts, it's 3 blocks in size, and you enter it somewhere. Now, the problem here is obviously fragmentation. So like with memory allocation on the heap, you have the problem here that you have to find a contiguous, range of 3 blocks that's big enough for your file. And then when you delete it again, you might have problems because you might have 100 blocks free, but not 100 contiguous blocks. So either you do something that MS-DOS did regularly and even early Windows systems on FAT, which was called defragmentation. So defragmentation was used in FAT, not to solve the contiguous problem, because it was not contiguous, as we'll see in a bit, but to improve access speeds, because files that have data in contiguous blocks are faster to read on a regular hard disk because you reduce the seek overhead and the rotational delay. But for this first contiguous storage, as we see in the first picture, it's absolutely necessary to do this defragmentation from time to time to enable large free blocks. Obviously, this is a sensitive operation, which has to be atomic. So this has to be either done in offline mode, or you could just use some other this sort of file storage, which would be recommended. Of course, these other file storages imply that there's a bit more overhead to do. So one more interesting thing that worked pretty well are linked lists. So in addition to data, each of your file data blocks contains a pointer to the following block. So this is used in relatively simple file systems, like the file system used on the disks of a Commodore 64 home computer in the 1980s. So there a block was 256 bytes in size, which would have been very convenient, except for that two of the bytes, the two first bytes in such a block, were used as a pointer to the next block of the file. So you had to split your data into blocks of 254 bytes instead of a nice 256, which is a power of 2, obviously, and then write it there. And the floppies there were absolutely horribly slow, so a couple of hundred bytes per second. So it wasn't a lot of fun, especially if those files were split over the disk. So you already had tools doing defragmentation of floppies there, which kept your disk busy for half an hour, but afterwards your files were faster. And even MS-DOS FAT, so the original file system behind MS-DOS, which could also use with whatever Windows NT now, and which is still very common on things like USB sticks or SD cards. This also used linked lists. So this used a file allocation table, which separated the linked lists from the block contents. So you could have nice and tidy 512 byte data blocks. And then this file allocation table list was separate. So another question, is block size decided by the file system, or does the disk have say in the matter? Well, it depends. So you can have devices which have a relatively direct way to access things. So this would mean you more or less write the bits on a track from the operating system. So this means you can actually freely define your block format. So if you have an Apple II, so the not very first, but the second computer built by Apple starting in 1977, this actually did most of this disk handling in software. And there were lots of programs that used different definitions of block sizes, of gaps between blocks, of block orderings and stuff in order to either improve the performance, because the original performance of Apple's DOS system was not so great, or to implement copy protection methods, which was also interesting. So I remember as a kid in high school, I started reverse engineering several copy protection methods because, well, we wanted to copy these games, obviously. And I still fondly remember playing pinball. Sorry. Nevertheless, you can do this on old computers. You can do this when you have a simple floppy controller. So you can do this on floppy disks. You could also do this on MFM hard disks. So for example, several vendors figured out that you could actually store more data on a disk, like you had a 20 megabyte disk with a traditional information encoding method called MFM, modified frequency modulation. And there was a new method which required a new disk controller, which allowed you to store about 50% more information on the same disk called RLL. So you could just sell the same disk as a 30 megabyte disk and ask for more money by doing these low-level modifications because you had access to the controller. More modern disks transfer data in blocks. So a SCSI disk, for example, or a SATA disk, you only send the request like, give me block number 4711, and it returns this block. So there you usually get a 512 byte block for historical reasons. Blocks are usually a power of 2 because they somehow nicely align, obviously, to what you can count. So that was the reason why blocks on a Commodore 64 were 256 bytes in size, because, yeah, well, this was an 8-bit CPU, so it was very easy to count up to 255 from 0, so you could count 256 bytes. But if you had a block that had 258 bytes, so 256 bytes of data plus 2 bytes of pointer to the next block, that would have been much more complicated. And people had trouble with this because more recent drives to improve performance, more recent disk drives use 4 kilobyte blocks. So this doesn't really work with all stuff like old bootloaders or things. And these disks actually have an emulation mode. So they start up as 512 byte block disks, but they actually just fake it and internally use 4 kilobyte blocks. On SSDs, it's different again, because that depends on your disk controller. So modern disks really require you to use the block size. On older systems, you could hack it yourself. And that was a lot of fun because you learned a lot about things like data encoding how all that stuff worked. And that's a bit of a shame that for most of you, this is relatively inaccessible because there's so many levels of abstraction on top of it. So MS-DOS FAT was still a simple system, and you could use tricks, as I said, like defragmenting your disk just in order to make your disks access faster. Then we have index storage, like in the original Unix file system. So here we have these inodes or just index nodes, and Unix Unix developers are lazy, so they don't like to type a lot. So that's why we have create without the A, and we have inodes instead of index nodes. So here we distinguish between two sorts of blocks. So we have the inode blocks, which are special disk blocks with numbers of data blocks belonging to a file. So each file is represented by a root inode. And then if this file is larger than what fits in the root inode, so usually 10 so-called direct blocks, which just contain a pointer, so a block number to block 0, 1, 2, 3, 4, up to 9 of that file. And if we need more space, then we use indirection. So we can use a single indirect block to point to another inode block, which then contains a number of pointers. You can have double indirect blocks, which has, well, 2 blocks in between, and we can even have triple indirect blocks. And you notice this enables you to store a large number of blocks inside of a single file. So these multiple levels of indirections are trade-off between, like, how large do I have to make my inode? Like, do I have to make it as large as as required to fit all the data blocks of the largest possible file? So that would waste a lot of inode space. Or do I do it in this way and then just use space as required? This also enables something interesting in Unix called a sparse file. So for example, you want to create a disk image for a virtual machine. And this could be 10 gigabytes in size. So 10 gigabytes is a lot of space, obviously. And what you can do in the beginning is to create a sparse file that just contains the last block of the file at position like 10 gigabytes. And then you can leave the rest empty. So this file would initially only use 512 bytes of storage. And then it uses more and more space as you fill up the storage. Of course, if you write all of the blocks, it will take up the 10 gigabytes. But if you leave blocks as 0, and that's the default for sparse files, then, well, you don't need an inode entry because the OS assumes the pages are 0. By coincidence, this works very similar to virtual memory, where you can also have pages, and your page table is also structured in a similar way. Though in a page table on Unix or on most systems, you always have the same amount of levels between your root of then your virtual memory system and the final pages or the final entries that refer to pages. But the idea is very similar. So we have this index storage here. So essentially, this means a file is just an inode number. So a directory entry is now just pointing to an inode number. And then the system has to go through the inodes to figure it out. And then we can also use approaches from databases, so tree-based storage. And this was used to efficiently retrieve records in databases, and it can also be used to find so-called chunks, so parts of a file in a file system. So the idea in B trees or related things is to actually store some index information in the nodes itself. So on the top level root node here, everything that's less than 9 or less or equal than 9 is contained in a separate block to the left. Everything between 9 and 21, so 10 to 21 in this case, is contained in something that's pointed to by the middle, and everything larger than 21 is in a block to the right. And then you can have hierarchies again to point to blocks. So this is also relatively ancient. So Apple used it, for example, in the second file system for the Macintosh, the so-called HFS hierarchical file system. So the very first file system for the Mac in 1984 actually just used a single level of storage and then just simulated directories, what Apple calls folders, by having entries in a list, which is a bit strange. If you look at my GitHub, I wrote a reader to read Apple MFS disk images. This is a very simple thing, but very strange. And Apple figured out as disks grew larger, so this worked well on a 400 kilobyte floppy disk, but then floppies grew larger to 800 kilobytes, and the first hard disk was 20 megabytes came out. This was not sufficient, so they wrote a file system from scratch, and this was called the HFS hierarchical file system because it now really supported real directories. And this is actually based on a variant of a B tree called a B star tree. So if you're interested in this, there's a nice book by the guy who implemented this and later also the file system for the BOS. This person is called Dominic Giampaolo, I think. Sorry for mispronouncing his Italian name. And this book is called Modern File System Design. So I think it's available freely as a PDF on the internet, legally. And if you're interested, this is a very good book telling you how to design file systems based on like around 2000 state of the art, but still very much interesting because B already tried a number of new approaches in their operating system. And the Haiku operating system still supports this today as the open source version of BOS. So the problems we have to solve as an operating system, we need to manage, of course, the directory hierarchy, but also the free space on disks. We've seen a lot of approaches for free space management. So a very simple approach, for example, used by the original Unix file system is bitmaps. So for every block on your disk, you have one bit representing that block, and that bit can be 0, indicating that block is free, or 1, indicating that block is used. Or maybe it's the other way around. To be honest, I have to check, but that doesn't matter. You can also have linked lists of free blocks, or as with directories, you can also have trees of free blocks to handle them in a more efficient way. So bitmaps, again, of course, have the problem of taking up as much space. So 1 bit for a block. So quite a lot of space on your disk, depending on how big your disk is. And linked lists and trees of free blocks then reduce the storage space, but increase the search time to find a new block that's free. For directory managements, we have lists in FAT or in traditional Unix. So directory entry on FAT has this classical MS-DOS style file name. So 8 characters file name, 3 characters of extension. So if you have a file mytext.doc for a Word file called mytext, you write mytext and then, fill it up with space characters until you hit 8 characters. Then the dot is never stored anywhere in a FAT file system. It's implicit, and then you have doc as the 3 characters of the extension. That's also the reason why you can't have more than 3 character extensions unless you use extended file names. And then you have several attributes like read, write, and so on. You have a creation date, last access date, last change date, first data block, and length. Unix file system entries relegate most of that information to the inode. So Unix directory entry in, for example, system 5.3.2 from 1980 something just has a 16-bit inode number and a 14-character file name. And you see also here a power of 2 comes into play. So each directory entry is neatly 16 bytes long. So you could fit 32 directory entries into a 512-byte block. So this, of course, has 2 constraints. First, the inode number can only be 16 bits large, so you can only have 65,563 inodes on a given file system, which back then, given the size of the disk, was a large number. But, of course, somebody managed to exceed these numbers, so that didn't work. And you could also have only 14-character file names, which is a bit more flexible than the 8.3 because you can have as many dots in the file name as you want, for example, but still it's only 14 characters. So essentially, especially in Unix, people try new approaches, of course, also in NTFS and Windows. So you can have hash functions for directories, and you can also have lists with variable names. So just, again, an inode number, a name length, and an offset to the next entry, and then the name of more or less arbitrary size. There's one question. When is it possible to ask questions for the Q&A? Well, usually after I finish presenting stuff from the lectures here, and also Espen will be available for helping with the exercises at 2 o'clock. as he mentioned in the email you should have received today. So we have some challenges for file systems: reliability and performance. So reliability, I'm giving this bathtub curve here, which is an important curve you will see in many engineering problems. So essentially, you have an early failure period. So when a device like a disk just comes fresh out of the factory, maybe you can't test it completely. So there might be a number of undetected problems which are figured out relatively early, and then this stabilizes for quite a time, and then really hardware, for example, starts to degrade. So you have mechanical tolerances, you have things that start to break. So you have a wear out period at the end, and that looks like a bathtub, and that's typical for devices. So disks can and will degrade or fail, even SSDs, because you only have a limited number of write cycles. Systems can crash and just leave information in an inconsistent state. You want to prevent data loss, you want to ensure integrity. And we've seen methods like backups, checksums, and repair tools like fscheck on Unix to help with this. We've also seen performance challenges, so especially disks with mechanical components have low rate write speeds and high positioning latencies. And we have caches as solutions for this. And we also have the problem of like, my disk is not big enough, I want everything on one file system. So can we actually have a file system span multiple disks beyond the size of a single one without just buying a new bigger disk, obviously. So as problem solving latency or some latency and throughput problems, we see the Unix buffer cache as a buffer for disk blocks and main memory. So these use algorithms similar to page frame handling for virtual memories. And we've seen some optimizations there also, like read ahead. So if we figure out we have sequential access to a file, we can already load subsequent blocks of a file into the buffer cache before the application actually requests them, because we can speculate like, this will be used in the future. And we can also use lazy write, so we don't have to write all the data immediately to disk, but we can just keep them in the block in the buffer cache and write them out later. So for example, to write out data that was be written into a file sequentially in one large operations here. So this write back from cache happens either if your cache is full, or you should do it periodically. So if your system crashes, you minimize the amount of data you lose, because this data has only been stored in RAM in your buffer cache and not on disk. You can do it manually using the sync system call, or you can also use it as an option. So when you want to be absolutely sure your data arrives on the disk, you can use the OSync option when opening a file. Now, absolutely sure in this case means it's absolutely sure in the cache of your disk drive, because your disk drive also has a cache to accelerate accesses. So essentially, when you have the unlucky situation that you have a power file, when data is written out of the buffer cache to the disk, but the disk hasn't managed to write it back, well, that's a problem. So very often disks contain like something like a capacitor to at least allow it to shut down regularly, but maybe sometimes not all data in the cache manages to be written out completely when the power is gone. So we've seen logical volume management to remove the one-to-one relation between file systems and disks. So now a single file system can support multiple disks. So this helps with a situation that's not solved by mounting, because with mounting, of course, you can add space to your file system, but only under a certain directory. And here you could also, for example, have a very large file on a file system on a single one spanning 2 or 3 disks, for example. So this is done using logical volume management, where you can define something like volume groups that look to the operating system and to your application, like a single big disk. And then we've seen RAID systems. So the idea here was to save costs by creating large logical disks out of inexpensive smaller disks, which enables you to utilize the bandwidth better, and you can also have redundancy. And we've seen variants here like hardware RAID. So that's a disk controller with special management software and potentially some cache. We have a software RAID as a layer between the disk driver and the file system code. And we can have different RAID levels, which differ in throughput and in reliability. So here are just some of the most commonly used examples. So RAID 0 is just performance improvement. This is striping, so you connect several disks in parallel. This increases the bandwidth obviously, because you can read data from 3 disks in parallel. But of course, you also increase the failure probability by a factor of n, because now you have only 3 disks. So if one of these fails, some of your data is lost. You can have RAID 1 or mirroring. This means that you store each disk blocks on 2 disks. So on disk 0 and on disk 1, you have identical copies of each blocks. This increases the read bandwidth because you can read block 0 from disk 0 and block 1 from disk 1 at the same time. Sometimes you lower the write bandwidth depending on, like, if you have to access disk 0 and 1 for writing each copy of a block separately. But you have higher reliability because now one of the disks can fail and you can still have a copy of all the blocks, and then you can distribute stuff over a number of disks with like RAID 5 and 6 with distributed parity. This usually gives you increased performance. You have increased fault tolerance because now, like, one of the disks can fail and you can still run the other ones. It's not as good as with RAID 1, but it's less expensive, obviously, because you don't waste 50% of your space. And you have additional write overhead. But RAID 5 is the most used RAID system today. So then we had to look at more modern file systems like journal and log structured file systems. So the idea is that in a file system, if you just write the changes that happen to files, in addition to writing data and metadata, then you can have something like a transaction. So this problem, is my data written on disk or is it not written on disk, can be solved here. So this means either a change has appeared on disk completely, which means not only data I write to a file, but also all the metadata like file size, access date, inodes belonging to a file, and all that stuff has been changed in one operation, or it has not been changed in one operation. So you can still have data loss here, but at least you have consistency, which means with a journal file system, you usually don't need this file system check step in case your system crashed or you had a power failure and you want to start it back up again. So you don't need this file system check to run the integrity. You just have to what's called replay the journal to check all the entries, and that's much faster. And then you can have log structured file systems. So this is actually a radical version of journal file systems, which means that, I actually don't need to write any data blocks in a regular file if I have this log. So this log is sufficient for everything. So blocks are not overwritten, but just all changes are just appended to the log. And also changes to metadata are also stored in the log only. And of course, then you can store write operations just in a large segment of your main memory and write them to disk as a single large segment. So that's faster, but of course it makes managing the file system more complex. And then we finally had a look at COW, or copy on write file systems. So this is what's used in very modern file systems like ButterFS or ZFS from Sun. And these actually refrain from overwriting anything. So that's an idea from log structured file system, but it's more flexible when allocating free areas because you can do it, for example, in a B tree again. And this is actually very nice, but it's very complex. So this would be something we would look in detail, for example, in an advanced operating system course, but just to let you know, stuff like this is out there, and that's mostly state of the art nowadays. Now, Microsoft actually tried to produce a new file system for Windows NT based on their database technology. WinFS was called. This never materialized because they had so much trouble actually getting it to work correctly and performantly. So all these copy and write file systems are relatively complex and also sometimes have very high demands on the hardware. So for some use cases, like small embedded systems or something, these small file systems might just be the easiest, simpler file systems, might just be more convenient. So that was a quick overview of what we talked about in the videos last week. So accordingly, the theoretical exercise is all about file systems because they're a central part of most systems nowadays. There are very few systems that operate without a file system. So very small embedded systems, for example, can have everything just point as pointers in RAM somewhere as objects from your single application. And there's also operating systems running on so-called object stores like Smalltalk or list-based operating systems. These have a bit of a different approach where For example, every object is accessible in a large virtual address space like 64 bits. We're not talking about about details on these, though that might be interesting. So if you're interested in that, get in touch. I can give you some links to this. And of course, we've seen file systems are crucial for some non-functional properties of an operating system like performance, latencies, and throughput, and reliability. So that's all for the overview today. So now if you have questions on lecture contents, on exercises, whatever, feel free to go ahead and, well, ask questions, preferably in the chat. Of course, questions about the exercises can also be well asked, well, Aspen later in the session or now, or in the forums. As you know, we have all these ways to get in touch. So, no questions? Did you all get your web servers to work already? Okay. I hope you can still hear me, or is there a technical problem? Because I can't see any feedback on the chat. All right, as you can hear me, that's great. All right. So there's some specific problems someone is uncertain of. If you wish, you can discuss them with Aspen later in the session, or now, whatever you prefer. But maybe if there's specific problems, I'll just stop the recording now and we can discuss them offline or still online, but off the video. Okay, recording is stopped now.